Okay, so we have here a word problem on continuous distillation design using Ponchon-Savarit method. Okay, so the problem states that, okay, for a while, the problem states that there is a liquid feed of 100 kilomole per hour of benzene toluene mixture at the boiling point, um, which contains 55 mole percent benzene and 45 mole percent toluene. It is being distilled at 101.32 kPa pressure to give a distillate with XD, or the distillate composition of 0.98 and bottoms composition of 0.04. So using a reflux ratio of 1.3 times the minimum and enthalpy concentration method, do as follows. So we have to determine the theoretical number of trays needed to calculate the condenser and reboiler heat loads, and to determine the minimum number of theoretical trays at total reflux. Okay, so I have created here some rough steps to help us be guided in our calculations, but I don't recommend that you always cling on to these steps to solve any Ponchon-Savarit related problems. I just created this guide for us to be more organized and to be more neat in terms of how we deliver our solutions to word problems related to Ponchon-Savarit. So it's not really applicable all the time. Okay. So of course, before we perform the stepping off, the determination of theoretical number of trays needed, the first thing that we have to do is to perform mass and sorry, to perform mass and mole balances to determine the amounts of and compositions of entering and exiting streams. So it's a very important thing to do because the information that we get after we perform overall and component mass balance, we're going to place that in our enthalpy concentration diagram, or we call it HXY diagram. So I'll color this. What color do I like? I think this one is better. Okay. So I'm coloring this or highlighting this sentence to, indicate that we're going to do that step. Okay. So the first thing that we're going to do is to perform mass um, mole or mass balances. Okay. So I'll use this one. The feed, the amount of feed is 100 kilomoles per hour. Okay. I think it would be better if I make the drawing bigger. I downloaded a drawing from the internet in advance because I don't want to be burdened by um, drawing a faulty image. Let me write it again. Okay, so the feed composition, the entering feed stream has a flow rate of 100 kilomoles per hour, and it has a composition of 55 mole percent benzene and 45 mole percent toluene. So we are going to have we're going to have an agreement here that we're going to report um, concentrations of benzene only. Okay, concentrations of benzene only. So the mole fractions that you're going to see are only for benzene. Okay, to make us more organized and to um, because I think the diagram later will use benzene as the mole fraction, so it would be wise for us to report only the benzene. So the mole fraction here is 0.55, and as for the amount of distillate, okay, sorry. Do we have the information on that one? I think not yet. So we don't have the amount of distillate, but we have the uh, expected composition of distillate which is 0.98, and we also don't have the value of the bottom stream. Okay, but we are expected to have, okay, xb equals 0.04. Okay, I'm changing this one to xb, okay, for a while. Yeah, just to clarify things. Okay. All right. So of course, this is very basic chemical engineering skill. You have to perform overall and component mass balances. So let's start with the OMB, overall mass balance. In this case, it's mole balance, sorry. So overall mole balance, OMB. Okay, so let's the OMB for this one is, okay, yeah, it's always the feed equals the distillate plus bottoms. Okay, super basic. And then we're going to do, okay, so the feed is 100 kilomoles per hour. So that will be our first equation, equation number 1. And then our component mole balance, okay, component. So I would like to emphasize that the component that we're going to balance for this one is the benzene. Okay, yeah, component mole balance. So we also call that one as CMB, or the mole balances. Okay, the next thing that we're going to do is to do the component mole balances for benzene. So we have here XF multiplied by the feed equals the mole fraction of the distillate multiplied by the D plus the mole fraction of your bottoms multiplied by your bottom stream. So you have here the values of XF, which is 0.55 multiplied by 100, and then your XD, okay, that's 0.98, right? Okay, 0.98, and then your distillate is unknown. Yeah, it's unknown. Oops. Okay. And then your bottoms is 0.04 mole fraction, and then, okay. So the final equation is 55 equals 0.98 D plus 0.04 B. Okay, that's equation 2. Okay, so you can pause this video to answer or to solve equation number 1 and equation number 2 simultaneously to get the values of D and B. Okay, so let's pause the video. You can pause the video and then, yeah, compare our answers. So if my answer is wrong, please report it in the comment section. Okay, so that I can change or overhaul everything. Okay. Okay, so my answer for this one, okay, is the value of my distillate is 54.26 kilomoles per hour, and my bottom stream is 45.74 kilomoles per hour. Okay, I don't like, okay, it's not written properly. 45.74 kilomoles per hour. All right. So I think we're ready for, we are going to use that one later in our calculations for the condenser and reboiler duties. Okay. Okay. Okay, so the next thing that we're going to do is to, okay, we're done with the D and the B. Okay, the next thing that we're going to do is this one, to find the delta E min in the diagram to determine the minimum reflux ratio. So you have to note down that we have to look for the R min here because we cannot proceed with the stepping off if we don't know the value of our R. Because if we don't know the value of our R, we cannot solve for delta E. That's the important thing. So the challenge here in the problem is we're only given, we need to know, or we are forced to know we are forced to determine the value of R min, because if we know the R min, we can know the value of R, and if we can know the value of R, we can then solve for the value of delta E. And that's the only way that we can start doing the stepping off for the actual number of trays. Okay, so let's start in this one. Okay, let's start in the second step we're in. We're going to find the delta E min in the diagram to determine the minimum reflux ratio. Okay, let's color this one to indicate that, okay, we're in that step. Okay, so the challenge here is to locate the feed point first. So we know that the XF is 0.55, but we don't actually know, um, but it was stated here, okay, we actually know, sorry, that it is in the boiling point. So, at the boiling point, okay, I need to emphasize this one. So, as what I have said, as what I am about to say, we need to know actually the concentration as well as the value of the enthalpy of the feed. But since it was stated in the problem that it is a liquid at boiling point, then this is a saturated liquid. So we need to emphasize that since this is a liquid at boiling point, the feed is a saturated liquid. Okay. So that will affect that will affect the location of your feed point in the diagram. Okay, so let's locate the feed point in the diagram first. Okay, I would need to, okay, I would need to emphasize this one. Okay. The next is, next after locating the feed point, we need to find a tie line that will pass through the feed point. Okay. So I created a diagram, specifically the enthalpy concentration diagram for benzene toluene mixture in a separate Word file so that I can easily navigate through the lines as well as locate the points. So for this one, I am expecting that I will be exceeding the uh, typical graphs for the enthalpy concentrations as well as the graphs for the XY diagram. So just to remind you, this is a combination of HXY diagram, which is this one, and this is the XY diagram below. So if you ask me why am I using HXY together with an XY diagram, the purpose of that one is for me to locate the tie lines or the equilibrium lines which the HX diagrams do not do not have. I mean, most HXY diagrams do not have tie lines. So it must be coupled with XY diagrams at the bottom to guide us with the tie lines. And as you can see here at the leftmost, the left bottommost part, and the right topmost part, there are some extended calibrations because I am expecting that I will exceed the calibrations placed here by, or the set calibrations of the graphs for HXY. So the calibrations in the left and the right are only intended for the HXY diagrams and not for the XY diagrams. Okay, so first things first, we need to locate the feed point in the diagram and find a tie line that will pass through the feed point. And just to say it again, the feed is a saturated liquid. So we need to locate that point. I'm not sure if I can insert a dot here. I think I can. So if I'm going to create a small dot, okay, let's zoom in. Okay, I'll change the outline to no outline, and then the fill to let's use color blue. Okay, so the feed composition is 0.55, so it's 2 4, okay, it's here, and it's a saturated liquid, so it must be placed here. So the reason why I place it here in the red line, it's because in the HXY diagram, the red line corresponds to the enthalpy values at saturated liquid compositions, like pure liquid, and then they are about to, start forming vapors. And for the blue line over here, these corresponds to the saturated vapors. So if the feed is a saturated vapor, then I should place the dot here at the top. If it is a superheated vapor, of course I will place it here in the space above the blue line. And then if it is a subcooled liquid, I will place it here below the red line because it's a subcooled liquid. If it is a vapor liquid mixture, then I will place the dot in between. Okay, I hope that's clear. Next is to find a tie line that will pass through the feed point. Okay, so that will be an interesting thing. So this will be the part wherein the XY diagram will play a huge role as to how we're going to use it. Okay, so this is how we're going to use the XY diagram in this step. Okay, so this will be our guide for the tie line. So what I'm going to do to create a tie line to create a tie line in the middle, okay, based from the XY diagram, I need to extend, okay, a particular line from the feed point up to the equilibrium line. So I will extend first a vertical line. So what I'm going to do is locate the feed point. Okay, apologies if it is not really it's not really super accurate. Okay, and then I'll just color it, okay, maroon. Okay, so that's the feed line. That's the extended vertical line for me to touch the equilibrium line of the XY diagram. After I touch the equilibrium line of the XY diagram, I need to create another horizontal line from this point over here, okay, and then extend it to the 45-degree line. I need to make sure it's accurate. It's okay, I can't see it clearly because they have the same color as the equilibrium line. So I'll change it to maroon. It's somehow not so, not so close. Yeah, but I think this will do. But I'm still, conscious. I want it to be really exact. Okay. Okay, apologies if this will take too much of your time. Oops. Okay, it should not be the case. The problem with this one is that I need to really focus the here. Oops. Okay, anyway, okay, assuming that's the correct line. Yeah, it's so difficult because what we have here is not a picture of a graph. Like, it's really a working diagram. So it somehow disturbs how we navigate the lines here. So okay, so assuming, okay, let's just make everything far so that we can assume that it's correct. So after I make the vertical and horizontal lines, I will extend another vertical line from the 45-degree line over here, okay, up to the point where I can touch the, okay, HY diagram or the blue line. Okay, so actually what I'm doing right now is I am looking, or I am determining the corresponding value of the vapor phase, or the equilibrium mole fraction of the vapor phase that will exist together with that exists together with this point over here in the feed point. Okay, so what I'm actually doing is I'm creating a tie line in between the HXY diagram. Okay, in the space between the HX and the HY. So the tie line here is actually this one. Okay. Yeah, so I'm not really sure, guys, if it's super accurate. Yeah, but I would really it would be really nice if you do it, like manually, so that you can use actual ruler measurements. Okay, so yeah, that's the tie line for the the tie line that will pass by the, or that will pass through the feed point. Okay, that's what it meant in the second step. So this is only a guide for the tie line, so it's not really, we don't really need to use that here. So I think I can delete the lines. Okay, so that we can, because we are going to make more lines later. How am I going to remove you? Okay, here. It's already removed. So that's it. We have already the tie line for... Okay, I think I need to increase the weight. Because if you increase the weight, it's easier to have a grip on the line. Okay, that's the extended tie line. That's the tie line that will pass through the feed point. Okay, the next